Beautiful. So we didn't have audio that entire time?
Yeah, the entire time.
Great.
Sorry.
Awesome. We missed my very good intro that I did. But anyway, now that you can actually hear me, it's 3:30. We do these shows every day. Keep tuning in. They're great. We're talking about water and salt today. And so we are, what I'm showing here is a model of a bunch of different water molecules. And this is sort of representing water in its liquid state, where it doesn't have that necessarily really regimented structure that you see when it's ice, but it's not just a bunch of individual molecules floating around. Instead, it kind of forms these little bonds, these little clumps, these little rings all over the place. But what's important about the water molecule is that it is what we would call a polar molecule. And when we say polar, what we mean is that it has one side that has a positive charge on it and one side that has a negative charge. And so in the case of water, the H side, the side that has the hydrogens on it, is the positive side, and the O side, the side that has the oxygen on it, is negatively charged. And so that's what helps all these molecules kind of bond together, is that negatives are attracted to positives, positives are attracted to negatives. But what we're talking about is salt, and one of the things that being a polar molecule does for water is it makes it what we would call a really good solvent. It is really good at dissolving other things in it, a thing that you dissolve something else in is called a solvent. And so in particular, it's really good at dissolving things that are also polar like it is. And so in this case, what we're talking about is salt. So salt's formula is NaCl. The Na stands for sodium, which is what the blue ball is representing in this model. And the Cl stands for chlorine, which is what this is representing, the green ball. And in the case of salt, the sodium is the positively charged end and the chlorine is the negatively charged end. And so what happens when you introduce some salt into an amount of water is that the positive sodium gets attracted to the negative oxygens, and the negative chlorine gets attracted to the positive hydrogens. And what is liable to happen when they start glomming on to the salt is that all these water molecules, all these chains of water molecules are going to keep moving around. They're not just standing still in here. They're sloshing around like water does. And what's liable to happen is that your salt is going to get ripped apart. And what happens then is you no longer have, I guess, salt. You have a sodium atom and a chlorine atom. And so when we say something is dissolving, that's what we mean, is that it's kind of getting ripped apart by the stuff that you put it in. The other thing of note, of course, is that when you get down onto a really teeny tiny molecular scale, there's space in between here. So you might end up with a situation where, you get a couple little bit of salt that you're throwing in, and, it doesn't just necessarily glom right on here. It ends up filling in some of these gaps here. So sometimes when you mix a thing into another thing, those volumes end up not just adding together, because sometimes the salt is slipping in between the other stuff. But anyway, that's just a preamble to, excuse me. Sorry, I actually have to take this. Hey.
All right, I'm going to fill in while Ryan is indisposed. And so, as we were talking a little bit earlier, I'm going to play with these magnetic molecules for a little bit until Ryan gets back. So, as he was saying, these magnetic models represent water molecules, and water in its liquid state really likes to form what we call rings and chains. So these things are going to hang out like this, and that's how we get drops and drips and rolls and things like that. And I'm going to swing it back to Ryan.
Thank you. Sorry. Urgent matters, Anyway, we're talking about how when we mix salt into water, it doesn't necessarily always equate to a completely just additive process, because it kind of fills in the gaps sometimes. And so, with that in mind, what I have here is 250 milliliters and 250 milliliters of water fresh from the tap right here at HSC. And what I have in here is 5 teaspoons, or 25 milliliters, of salt. And so what I'm going to be doing is adding, well, why don't we start here? Let's add a couple drops of food coloring just for visibility's sake in here. 2 drops of green into that one. 2 drops of red into that one. And now what I'm going to do is I'm going to dump my 25 milliliters of salt into, we'll do it into the red one here, into my 250 milliliters of water. And like I said, what you might expect is when we add our 250 and our 25, what we'll end up with is 275 milliliters of stuff in this particular beaker here. Do a little stir in here, get our colors mixed. And that would be true if we were just adding more water. If we had 25 milliliters of water, it's 250 milliliters of water. You end up with 275 milliliters of water. We'll see if that's actually true when we do it with the salt. So we'll pour our salt in there. Put that off to the side. Stir it up. Make sure it's good and dissolved in there. So like I said, when we're pouring the salt in and stirring it, all those NaCl molecules are getting torn apart, dispersed amongst all of our water here. And you can see it made a difference in the color of our water too. It kind of got this weird kind of cloudiness to it. And what are we seeing here? So if it had been a direct just addition, we would have gone from this line where we were before all the way up to this line. And you can see we're not quite there. So we added 225 milliliters, but we didn't quite get 25 milliliters of volume out of that. And so that's going to have an effect on our experiment that we're going to do next here. And so the reason we're talking about this is because over the last several decades, there's been a lot of additional salt introduced into a lot of ecosystems. And Minnesota has a particular issue with this. Especially in the winters, because of course one of the things we do is we pour salt all over everything because it helps melt ice, helps keep the roads safe in the winter, keep sidewalks safe, etc., etc., etc. It's you know, handy for us humans to get around, but we don't always necessarily think about the side effects of that. And that salt has to go somewhere, and in our case, most of it ends up in the water. And so it's good to know what adding all that additional salt is going to do to the water. And so what I have here is just a, standard piece of, store some old leftovers in it type of container here. Probably have something like this in your kitchen. I know I do. And then just a sponge, big old sponge. And what I'm going to do is kind of wedge this sponge in here so that I kind of have my tub divided in half. And this sponge is kind of big for this container, but it'll do what we need it to do. And now what I'm going to do is I'm going to take my 250 milliliters of tap water and my 250 milliliters of tap water plus 25 milliliters of salt, and I'm going to pour them on opposite sides of the sponge here.
Is your sponge wet or dry?
My sponge is wet. The sponge has to be a little bit damp for this to work. It's not soaking wet, it's not dripping wet, but it is a little bit damp. Helps keep it a little bit flexible and also helps keep our water from permeating it quite as much. Pour them both in there. Now, what we'll do is we're going to just pull that sponge out. And assuming I didn't mess it up too bad, what we should see is a little bit of what we call stratification in our colors here. So, gotta make sure I don't jostle it up too much.
If you hold it just a little bit higher and on the side so we get the white screen behind you, then we can see it really nice. Yeah.
Like that.
Yep.
And so, what you should probably be seeing there is kind of pinkish, reddish on the bottom and then green on top, right? It's working. So I haven't even really gotten a chance to look at it. Perfect. And so what that tells us, the fact that it's stratified like that, what that tells us is that the stuff in our red flask here, our water mixed with salt, is more dense than our stuff that was in our green flask here, our just regular old tap water. And like I said, that's important because that happens out in the wild too. And so when we add salt to a water system, if we dump a bunch of salt into Lake Bemidji, that stuff's going to settle towards the bottom. And one of the really important things that happens every, spring and fall around here is you get this big lake turnover that happens as the temperatures change, because that's another thing that's going to affect the density is the temperature of the water. Cooler water is more dense than warmer water. And so what you see as the temperature changes is that you see some turnover that happens in the lake where water from the bottom gets brought up to the surface and stuff from the top gets sent down towards the bottom. And with that comes a lot of nutrients that's really important for the health of the lake and the surrounding ecosystems. So when you make a big change to the density of the water at the bottom, that affects that turnover of all those nutrients to the point where just the temperature change isn't enough to make that turnover happen. And so that has a really negative consequences as far as, like I said, dispersing the nutrients around the lake like they're supposed to. So adding a bunch of salt to a lake is not healthy. It's bad for it generally. But the amount of salt that we have in the lakes here in Minnesota is rising pretty consistently and pretty substantially, but it's not at the level that we're seeing here. We added quite a bit of salt in here for the sake of making this effect work, but it is worth noting that this is an amount of salt that is in some bodies of water around the world. And I have kind of a second little experiment here. I don't know if experiment's the thing, a second visual here, where we have a scale. And this is the scale that we use for measuring the food that we give to the birds. They get a weight of food is generally what they're going to get. And so we weigh in grams here. So this is metric. So maybe it's not a scale that you're the most familiar with, but I'll translate as we go. And what I have on there is 0. And so what we're going to do is I have another 250 milliliters of mixed up salty water here, same exact mix that I had in my my red flask there, minus the food coloring. And so what we're gonna do is, a little stir here quick. What we're gonna do is we are going to weigh this. I'm gonna see how much this weighs. So before we do that, we need to do what's called tearing our scale. So if we were to just plop this on here, it's going to give us a weight. It's going to weigh 507 grams, which is a number that is maybe useful for somebody. But 507 grams isn't just the weight of that water, it's the weight of the water plus the flask that it's in. So we got to have a way to tell our scale that we don't want the weight of the flask, we just want the weight of the water. So what we do is we're going to put a new flask, a dry flask, an empty flask on our scale. Then I'm going to hit this tear button. And then what I do when I'm hitting the tear button is that's telling the scale, okay, what I want is for you to treat what you're feeling right now as a scale as weighing nothing. And so now when I add my water in, it is not actually it's not actually weighing the flask, it's just weighing the additional water. And water, particularly in metric, has a pretty easy weight to remember. So water weighs 1 kilogram, which is, 2 1/4-ish pounds per liter, and a liter is a little more than half a gallon. And so if we had pure water in here, the number that I would expect to see on the front of this scale, which I haven't read yet, would be 250 grams. So 1/4 of a liter should weigh 1/4 of a kilogram, which is 250 grams. And I bet it's not that. It is, in fact, 273 grams. So what that tells us is that we have our 250 grams of water in there, but then we have an additional 23 grams of other stuff. And in this case, most of that is the salt that I put in there. There's probably a little bit that's in there just from stuff that's in our normal Bemidji tap water all the time. We don't get pure, strictly just water molecules that come out of our tap when we use it. But that's a good number to know, because what that tells us is that the water that is in there, that salty water, is, like I said, has some other stuff in it. And we can use that weight to kind of think about how salty that is relative to other bodies of water in the world. And so 273 grams is, let's see, that would be like 1,098 or so, 1,096 kilograms. If we multiplied this times 4, it would be 1,096 or something like that kilograms, which is about 1/10 of the weight of this is just salt, basically, which is a lot. Like this is, if you were to compare this to something like the ocean, this has like probably 6 or so times the amount of salt in it that the average like take a scoop of ocean water would have in it. But it's actually not like the most of any natural body of water in the world. So this is like less than half as much salt as is in like the Great Salt Lake, for example, in a given scoop of water of that. Less than half of what would be in a scoop of water from the Dead Sea, for example. And so there is water out in the wild that is this salty and substantially more salty than what we have here. So it's not like, in order to get this effect, I had to add a completely unreasonable amount of salt into the water. This is something that is true at any level of salty, that it's more dense when it has salt mixed in with it. And like I said, going back to why this matters for us is, like I said, our water around Minnesota is getting progressively more salty. It's getting saltier and saltier every year. And as I mentioned, that has some far-reaching consequences that maybe we don't always necessarily think about, as far as, like I said, the nutrient turnover in the lake, but also just the survivability of the lake for, things like fish. There's a reason that there are saltwater fish and freshwater snails and saltwater snails and all these other things, is because they are dependent on, the water being a certain level of salty to be able to be functional. And so be mindful, I guess, is the big takeaway of this when you're spreading salt around on your sidewalks, your walkways. Be safe. We don't want to have slippery sidewalks. We don't want people out there slipping and hurting themselves. But be mindful of the amount you're using and how often you're using it. Because, as I mentioned, it's got consequences beyond just melting the ice on your sidewalk. And so I think we'll call that a conclusion for today. Thank you all for watching. Like I said, we do these shows every day at 3:30, so keep tuning in. We do them 7 days a week. Special thanks to the Beltrami Electric Co-op. They have given us is it a grant they gave us that is sort of underwriting this? We got some money from Beltrami Electric Co-op that's helping funding these at the moment, so shout outs to them. We are currently open 4 days a week to the general public, so we are open Friday, Saturday, and Monday. From 9:30 to 5. We are open on Sundays from 1 to 5, so come on and visit if you're general public. Come in then, pay some admission, come visit with us. I love having guests around. If you are somebody who is representing a group, we are actually accepting group visits as well on those days off, so Tuesday, Wednesday, Thursday. We are currently scheduling group visits, and we've actually been getting quite a few of them. So if you are representing a group and are thinking about maybe coming in, call in now and figure out what days are open, because those days fill up pretty quick, actually. What was the other thing I was supposed to remind everybody of?
The Best of Minnesota Star Tribune thing.
Yeah, so we, the Headwaters Science Center, have been nominated as the best museum in Minnesota by the Minneapolis Star Tribune. And so we have links on our Facebook and our website that you can go to if you want to give us a vote. We would really appreciate it. Get us a little bit more, a little bit of free publicity on behalf of the Science Center. It'd be great for us. So yeah, go give us a vote. We'd appreciate it. Otherwise, we will be seeing you tomorrow. Tomorrow is Friday. Yeah, so it's probably going to be Chuck talking about something, but could be anybody, who knows. But we, the Royal